questions? Oh yes, I haven't formed I. Yes, that's coming next. Very good. So I've got my R's, right? Now I want to get my I's. My R's, as I said, I may want for other reasons if I just want to evaluate a function on my grid. But yeah, the point here is to get these I's so I can solve Poisson's equation. And for the I's, since these are the values of my basis functions, I need to know what my basis functions are. These are my basis functions. But the other thing I haven't told you yet is what are my chosen G vectors, my reciprocal lattice vectors, that are commensurate with my periodic boundary conditions. So we have to specify those next. Then we can build the I. So the lattice vector is G. And we'll do this in a matrix language. The lattice vector is G. Now, most of you probably know the answer from Ashcroft and Merman, but you'll see in a matrix language it comes out much more quickly. So I kind of like going through this exercise. Okay, basis functions. So my basis functions have to obey, I want my B alpha of R to be periodic. And what that means is that e to the I G alpha dot R must equal, for all three possible lattice vectors RL, right? It must be the same as e to the I G alpha dot R plus RL for all three of those. And the natural thing to do is to factor out the exponent G alpha dot R times e to the I G alpha dot RL. You notice that these two factors are the same, so they can be eliminated. So this complex exponential, the argument here has to be an integer multiple of 2 pi. So we know then that G alpha dot RL must be 2 pi times some integer n and alpha L. I'll call it another list of integers like that. And let's now try to turn this into a matrix language. Well, G alpha dot, to do dot products, of course, the way we do that is we do transpose multiplications. The RLs, I may as well orient next to each other in my favorite matrix R. Like that. And then the result that I'm getting here is 2 pi times, let's see, here's the way I index it. I guess that's n alpha 0, n alpha 1, and alpha 2. Good. So one formula would tell me that if I want G alpha transpose for any of my vectors G, what I need to do is to do 2 pi times R inverse times my triplet of integers, which would be n alpha gathered into a vector with these 3 components, and it's transposed because I'm looking at a row vector expression. So that gives me all of my reciprocal lattice vectors. And this guy here, its rows, by the way, are just your normal reciprocal lattice vectors. So that's kind of neat. Okay, almost there. But, of course, in practice, we're going to want a list of all of those G alphas. I've got a list of my R's. Do I have a good expression for R somewhere? Yes, I do. Questions? Question?
The R inverse should go at the end.
Oh, did I? Oh, I'm sorry, getting tired too. N alpha vector transpose R inverse on the end. And I guess, some people prefer the transpose of that equation. You can just say that your G alpha is equal to 2 pi, what is it, R inverse transpose times your n alpha, if you like things that way. I like to compute all the g vectors. Sometimes we need those. Remember, we needed them to calculate the diagonal elements of the Laplacian. We needed the magnitudes of all those vectors, so we have to compute them. And the way I like to arrange them is just in analogy to my matrix R. I like to put G0 as the first row, and then G1 as the next row, and so forth. So this then will be, I've got my G0 transpose expression, right? It's 2 pi, so there's a 2 pi in front of everybody. Well, it's 2 pi n0 transpose R inverse, I believe is what it is, right? And then the same thing for all the other ones. And just like last time, certainly everybody carries a factor of 2 pi that can be factored out. I can then just make a matrix with these triplets of integers. And I like to call that matrix, no big surprise, a boldface n, and everyone's carrying the post factor R inverse. So if you want to compute all your g's, one of your lines of code is just going to be 2 pi times this matrix of integers n times the inverse of R. Got my g's. Good. We're cruising along. Any questions on G? All right. Last bit is I, finally. What is I? Oh, that hurt. So I had RP equaled R. All right. So I. E alpha equals e to the I g alpha dot RP. Our basis functions evaluate at our sample points, which is then e to the I. Oh, and remember, of course, dot product just means transpose the first column vector and multiply it by the second column vector. G alpha transpose is sitting here. That's 2 pi n alpha transpose times R inverse. That's G alpha. And RP is this guy. Is R times diag of S inverse times MP. Good. Right. So, something nice is happening here. I see a happy gentleman. What? Tell me what's happening. Oh, you never. You're happy for other reasons. Okay, sorry. Okay. And the one, sir, behind. Did you see something happening?
Is the R inverse R?
Yeah, the R inverse R cancels. That thing's very nice. Everything else here is just integers, right? So that means this thing, whatever it is completely independent of the size and shape of my box. So we did choose the correct natural set of sample points. That should make us feel happy. That's good reason to celebrate. The other thing you'll notice is as I write this out, this is e to the 2 pi I times, I've got two vectors, diag S inverse just divides all the elements of M by the corresponding, now Cyrus is happy, I know why he's divided by the corresponding elements of S, right? And then those just get dot product with the corresponding elements of N. So if I write that out, that's N0, M0 over S0 plus N1, M1 over S1 plus N2, M2 over S2. Yes. Okay. And then, can anyone tell me why Cyrus is so happy right now? Hopefully he's paying attention to my lecture and not texting somebody. No? Will Cyrus tell me why Cyrus is that? No? Come on, please, somebody. No. All right. What is this matrix? This is the kernel, yes? Yeah, it's the kernel for the forward discrete Fourier transform. Exactly. It's got 2 pi in one dimension. People might be more familiar with the 1D Fourier transform. You have 2 pi I over the size of the matrix, the size of your vectors, times each of the 2 integers. And that's the one integer indexing the output and one integer indexing the input vector. And that's your Fourier kernel in one dimension. And it's just an outer product to form it in 3 dimensions. So this is the kernel of the fast Fourier transform. So I is just equal to the Fourier transform kernel, which I like to call F. So that if you call the fast Fourier transform, you will be implementing the I operator. And you'll be multiplying by I. So, good. So that's that. Little piece. Wow, we are cruising along. And in our little crank turning process, we only needed 4 of these operators, right? We needed O, L, L inverse I didn't talk about yet. I should talk about that. And J. So J, if you recall, is just the inverse of I. And the inverse Fourier transform has a kernel which looks a lot like this. In fact, can someone tell me, for the inverse Fourier transform, how its kernel differs from the forward Fourier transform? You guys should know this from your continuum Fourier transform. The sign in the exponent, right? It's a minus I. So, in fact, the way I like to write that is just F star. F is a matrix star. We'll just flip all the signs on I. And then there's another thing, right? When you do continuum transforms, of course, there's this 2 pi cube factor that has to be in the right places at the right times, right? In the discrete case, that factor turns into 1 over, notice there's no volume involved because there's just, all integers here, but it's 1 over, say again?
It's not exponents.
Yeah, it's the product of the 3 sizes, right? So the product of the 3 sizes, in octave notation, you can just type prod if you want, prod of S. But the way you'll implement it, of course, is you'll just call the Fourier transform, inverse Fourier transform. So that's J. We've settled J. We've settled I. O is easy, right? L, I gave you, was diagonal, but we need L inverse. And that's the last of these operators. Then you guys can pretty much jump in and start coding, except for one subtlety known as Fourier aliasing. We'll see how much I can cover. But let's get L inverse out of the way. So L, I'm a little annoyed I lost L. Let's start right. I remember L. L was just a diagonal matrix. It's basically just G squared, right? Like it is in Fourier space. So L had, there was a minus sign. This is minus G squared. There was the volume factor, det R, and then it was diag of the G squareds. G0 squared stacked G1 squared to make the column vector, like so. Whew. Right? Now, we have to invert this. Well, it's a diagonal matrix. So the inverse, you just inverse the elements along the diagonal. And so we'll get minus 1 over det R. And then diag. We're just inverting the diagonal elements separately. G0 to the minus 2. G1 to the minus 2. And so forth. So it's very easy to invert L in this case. And that's why, as we said, we don't have to do a solver when we're using a spectral method for Poisson's equation. We can just multiply by that set of vectors. And that's one reason why spectral methods are so powerful. And the other comment I'd make is, by the way, this second half of this lecture, really what we've done is, in our language, we've learned a lot of our language, but we're also becoming experts in using the spectrum method as well. These are all the nitty-gritty details you need to actually do a calculation with the fast Fourier transform. So we're almost there. Okay. So that's L inverse. There's one little problem with L inverse. The first G is 0. And we're going to have trouble converting that. Right? Well, we'll get an and. That's what we're going to get. Right? We're an if probably. Well, fortunately, it doesn't matter. And that's what's nice for us in this case. If we look at the solution for phi of r in our basis expansion, right? It's the sum on alpha, phi hat alpha, e to the I, g alpha dot r, right? I'll separate out the 0 term. That's just phi hat 0, e to the I 0 dot r, plus then the sum of all these other non-zero g vectors. Right? And e to the I 0 dot r is just 1. So you'll see, because this thing is infinite, right, we're going to get an undetermined value for phi naught, but phi naught is just a constant added on to our potential. And Poisson's equation that we're trying to solve says del squared phi is minus 4 pi n of r, but also notice del squared of phi plus any constant is minus 4 pi n of r. So you can add any constant to phi, and you're going to get just as valid a solution. It's the usual arbitrary zero of potential in any problem. So it's no surprise then that Poisson's equation does not determine that constant for us. It just gives us some crazy nan when we run the calculation, because it's undetermined. We can't determine it. Turns out physically it doesn't matter what it is. So as a consequence, we just need to set this constant to something by convention. And by convention, we choose to set it, well, to 0, right? So 0 by convention. Question, or someone said something? 0 by convention. So when we implement this, all you're going to do is you will go through and do all these divisions, right? You're going to get a nan for the first component of phi, but then afterwards, you'll just set that nan to 0, because the first value phi, by convention, is 0. And then your calculation, you can go ahead and proceed. So that's the one subtlety involved here. Any questions? We're just setting the arbitrary zero potential. It's no big deal. Nothing to worry about. Nothing to see here. Move along. All right. Good. All right. Any questions? So we've specified all of our operators, with the exception of just one little subtlety, which is to actually code this up, you need to know what this matrix of n, what to actually put in that matrix. The rest of it is just a formula you can quickly code up. And also what to put in the matrix M, which I haven't written down here. But I'll write down M for you. Let's see. I'm getting a little disorganized. And these are the last little bits I didn't think I'd get to cover, but we might just. So the matrix M, as you recall, was just these triplets of integers written along as rows, where the elements in M just had to span the whole range between 0 and S0. M1 was between 0 and S1. And similarly for the second coordinate. We just have to list all of those possibilities to make sure we index everywhere inside our little parallelepiped. So there actually is, though, a conventional order that these have to be in so that when you call the standard fast Fourier transform routine, it actually does what it's supposed to do. Right? It has a certain order in mind. And here I'm going to tell you what the order is. It goes like this, basically. As we just said, you list the 0 vector first. Then you list, it's just like an odometer kind of thing, except the first column goes fastest. This has something to do with C and Fortran and DFTW package, and blah, blah, blah. So this thing counts all the way up until you get to S0 minus 1, which is the last value for the 0 column. Then this rolls over to 0, and this thing becomes 1, and this is 0. And then this guy spans all possible values while these stay as 1s, and these stay as 0s, right? You get the idea. Until finally, this is S0 minus 1 again, and then this will flip over to 0. This 1 will roll over to a 2, and it continues like that. Right? Until you fill in the whole thing. Until you get down to the last element is S0 minus 1, S1 minus 1, and S2 minus 1. And that's when you know you're done. Okay. Good. N. Now N, oh man, what am I going to do N today? N, can I do it? I don't think I can do N. I'll just tell you a little bit about it. I'll tell you what N is, and then I'll have to explain that in the next lecture. So N follows the same kind of pattern, right? Little odometer pattern. Everything's fine. Everybody's 0, you know. Minding their own business. Counts 1, 2, 3, right? And so forth. Until you get halfway through the list. Until you get to S0 divided by 2. Or, depends how you want to do it. Until you get to S0 divided by 2. So as a concrete example, if S0 were 8, you might do 0, 1, 2, 3, 4, but then something happens. Then, you know, because this is used to construct the reciprocal lattice vectors. Reciprocal lattice vectors come in positive number flavored and negative number flavored, right? You know, if you have one value of G, you'd like to have the corresponding minus value of G. The question is, where do those go in the sequence? Well, after you get up to 4, you jump around to minus 3, and then to minus 2, and then to minus 1. If I've done my job right, there are 8 numbers on the board. 1, 2, 3, 4, 5, 6, 7, 8. Right, and that's the end of the list. So after S0 over 2, you get to minus S0 over 2 plus 1. And then you continue until you get to minus 1. These are all 0 along the way. And then you're at the flip over point where this becomes 0, and this becomes 1, and this stays 0. And you start the process over again. And then this column has the same kind of funky feature, it rolls over halfway through. And finally for the third column. Now the reason for that is like a little 10-minute discussion. Now that's the thing I anticipated. There wouldn't be really enough time to draw for you. It has to do with Fourier aliasing. We'll talk about that in the first part of the next lecture. But you can, depending upon how your philosophy about living the dream is, right? You can now, if you want, do the assignment. Right? The assignment, the key tricky part in the assignment was understanding how to build M and N, and then knowing how much you care that you know that what the second half of N is doing right now. Depends on how much you want to dig into the assignment right now. I'll leave that option up to you guys. But I can explain this to you at the beginning of the next lecture. Any last questions? Yes, sir.
So we originally start solving the Poisson equation because we have some double integral, and we
Yes.
rewrite part of it. Part of it looks like the solution for the free space, like the n of r multiplied by the free space Green's function. But now we're doing periodic coordinates. How does that? Like we're solving a periodic geometry. So.
Let me see. How do I want to ask your question one more time? I'm processing it. I just want to figure out how to grab into it. So, okay, the free space Green's function, he's saying, versus the periodic boundary condition.
Yeah, because what we have in the calculation for the energy, it looks like something multiplied by the potential for free space with source n of r.
Right. The quick cheap answer for you actually is that the Fourier transform of the free space Green's function, right? And the, let's not call it G. Let's call it K for Coulomb with a K, only because I need to use G for something else, right? The periodic boundary condition Green's function, I would call, say, Kp, right? It only exists at discrete lattice vectors G, right? But it is the same thing as K naught, just evaluated at K equals G. Another way to look at this would be to say, well, basically. So I'm still doing the free space Green's function in a way. It's just that the source happens to be periodic. I guess that's easy. Now, I haven't quite asked the right dangerous question yet, but there is a little bit of a dangerous question here, and that's partly why Cyrus was amused a couple minutes ago, separate from the other time he was amused, right? Which is that this thing of setting this to 0 has to be done very, very carefully, right? This really only makes sense if the total density that you're solving for has 0 component at G equals 0. Another manifestation of this Coulomb problem is the fact that if you have a periodic system, its energy is infinite, right? But per unit cell, a periodic system has a finite energy, right? That's because it's extensive. If it's a periodic system which contains a net charge, the energy per unit cell then becomes infinite and divergent, right? And then, all of your Coulomb sums then become conditionally convergent, right? And you have to be very, very careful. Now, what's going to happen, and that's in the current assignment, is that to make sure our system is neutral, right now our system just contains the electrons. I'm solving for the potential from the electrons, right? So that system has an infinite energy per unit volume. There's a problem there. And that's reflected by the fact that this 0 inverse is going to hit a finite number. However, when I add in the nuclear charge, right, that will produce a neutral system. So there's a corresponding infinity in summing up the nuclear charges. You're going to make a calculator in the current assignment to sum up the energy of the nuclear charges. And that's going to contain this same convention to set its phi 0 equal to 0. And what that will correspond to is actually neutralizing each system with a constant compensating background. Right? And those two backgrounds actually cancel. Right? So it's a long, long story, and I've pulled out many hairs over the years getting it just right under certain conditions. Right? So it is a very tricky issue. But if we don't, fret on it too much, what we're saying here is all true, correct, and makes good sense. Good. Anything else? All right, guys, have a good weekend. I guess we're on Wednesday next, right? All right.